Hi, so this video is going to cover section 9.2, estimating a population mean, right? So in section 9.1, we already looked at estimating a population proportion and laid down the general, idea for calculating a confidence interval and what a confidence interval is. So we want to build upon that, but look at population means now. And there will be some subtle differences when looking at population means because they do act a little differently. So just as a reminder here, remember the goal of statistical inference, which is what we're doing now, is to use information obtained from a sample and generalize the results to the population being studied. As with estimating the population proportion, the first step is to obtain a point estimate of the parameter. The point estimate of the population mean mu is the sample mean x bar, right? So the point estimate that we're going to use is x bar in this section, and recall that you can find x bar by adding up all your data values and dividing by n, right? So that's what that equation here is, right? So now let's kind of think through, what the margin of error would look like. So, and just to recall, right, the mean of the distribution of x bar is going to be equal to mu, and the standard deviation of x bar is going to be equal to, sigma divided by square root of n, right? So if we want to build a confidence interval in the form point estimate plus or minus the margin of error, right, we could first, write this as x bar plus or minus e, right, where e is the margin of error. And thinking through this, right, the margin of error, just like last time, right, would be, we might think it might be z alpha divided by 2, and then it would be the standard deviation of x bar, right? Well, we know the standard deviation of x bar, so we could plug that in. So I would have, x bar plus or minus z alpha divided by 2, and then this would be times sigma over square root of n. Right? But something to think about is, we're doing a confidence interval because we do not know what mu is, right? The population mean. So if we don't know the population mean, we're obviously not going to know sigma. So what if we plug in s in its place, right? So, basically we're saying s is going to be approximately equal to sigma, right? It's going to be a point estimate of sigma. So if we plug that in, I would have x bar plus or minus z alpha divided by 2 times s divided by square root of n, right, is where that would give me, right? Now, I won't get into all the technicalities, but it turns out that, s is a statistic, and that's also going to vary, right? That's a point estimate for sigma, right? So s will also vary. So this model, using the standard normal model, the z distribution, doesn't take into account this additional variability. So it turns out that in this section where we're dealing with x bar, we're going to use a different distribution called the t distribution. Right? So the formal name of the t distribution is the student's t distribution. Right? So you can see here that if we do a simple random sample of size n, taken from a population that follows a normal distribution, then t is going to equal x bar minus mu divided by s divided by square root of n. Right? So this is going to follow the student's t distribution with n minus 1 degrees of freedom. Right? So I'll shorthand that by df equals n minus 1, right, where df stands for the degrees of freedom. So we need x bar to be the sample mean and s to be the sample standard deviation, right? So if we now want to look at some properties of the t distribution, so the t distribution, that graph, that curve, is going to look slightly differently depending on the degrees of freedom, right? So in other words, depending on the n value, it's going to look differently. the t distribution is going to be centered at 0, and it's going to be symmetric about 0 still. The area under the curve is still 1, where you have half of the area on either side of 0. Right? And as t increases or decreases without bound, the graph approaches but never equals 0. And then the area in the tails of the t distribution is a little greater than the area in the tails of the standard normal distribution because we are using s as an estimate of sigma, thereby introducing further variability into the t statistic. Right? And as the sample size n increases, the density curve of t gets closer to the standard normal density curve. This result occurs because of the sample size increases, the t of s gets closer to the value of sigma by the law of large numbers. Right? So the big thing that you want to think about is, when we find, probability of the area under the curve, that's going to be differently depending on how your curve looks, right? So if you look here at this graph here, the reason why we're using a t-distribution is because it gives a slightly different shape of the, like bell curve. It's going to look a little differently than the standard normal. So if you, pay attention here, like this dark blue line is a normal curve, and like this pink graph is a t with n equals 15, and the dark brown is t equals n equals 5, right? So notice if you look at n equals 5, if you look at the tails, that's the tallest graph on these tails, right? So it's going to give more area on the tails. So you can see how that area is going to be different, right? Like if this was my value I was looking at, the area of the curve for the blue, pink, or brown, right, those would be slightly different because you can see that their heights are different, right? And the area in the tails is going to be different. And then basically another something else to think about with this is as n gets large, it's going to look more and more normal, right? So like if you look at n equals 5 compared to n equals 15, the n equals 15 is a closer match to the normal density curve, right? So this is going to look very similar. We just have to keep in mind if you're using the t or z distribution, so that way you use the right calculator in StatCrunch, so that way you're finding the right area, right? So then objective 3, we're determining t values. So just like before, like if I wrote down, find z of 0.05, that's finding, if we have a z distribution, that's finding the mark where the tail to the right of that is 5%, right, equals that area. So we can use that same notation, that same idea. We'll just use a letter t instead of letter z to know that we're using the t distribution, and find that tail value, right? And don't forget that we need to know the degrees of freedom in order to calculate this area as well, right? So like if we look at example 1a, we're asked to find the t value such that the area in the right tail is 0.10 with 25 degrees of freedom, right? So in other words, what we're trying to find is t tub 0.1, where the degrees of freedom is equal to 25. Right? So to be able to find this in StatCrunch, you're going to go to Stat Calculator, and instead of going to normal, we're now going to go to t, right? The t calculator. So we're going to type in the degrees of freedom, which is 25. And we want this to be greater than, and I want the area to be 0.1. And then so this value here is my t-score, right, my t value. Right, so t.01 is equal to 1.316. Right? So in part B, we're doing something similar, except we want the right tail to have an area of 0.05 with 30 degrees of freedom, right? So we're finding t sub 0.05 with degree of freedom equal to 30, right? And of course, if it helps you to draw a picture, please do so, right? So trying to find this cutoff where this area is equal to 0.05, right? And so we can show that notationally with a t sub 0.05, right? So if we go back to my calculator, my degree of freedom this time is 30, and I want this area to be 0.05, and so I get 1.697, right, if we round to 3 decimal spots. Right, so then part C, it says find the t-value, so the area to the left of the t-value is 0.01 with 18 degrees of freedom, right? So, essentially what we're trying to find, right, so this is my t distribution. I'm trying to find this cutoff value here where this area is 0.01, right? Well, the t distribution is symmetric, right? So this area would be 0.01. So in other words, this value would be t sub 0.01, and this value would be negative t 0.01, right? Because it's just on the left, it would be whatever the negative of that is, right? So I'm trying to find this negative score, right? Because we'd have 0 right in the center. So in other words, again, I'm trying to find negative t 0.01, which that's going to equal negative, and then I can find that value in parentheses with a degree of freedom equals 18. Oops. Right, so I can change the degrees of freedom now to 18. I need to change this area to be 0.01. So I found that to be 2.552. Right, so 2.522. So then this would of course be negative 2.522. Right, so that's one way to find it using symmetry. If you didn't want to use symmetry that way, you could find this pretty easy. We just need to change this to be less than, and this to be 0.01 still. Hit and compute, and we get negative 2.552. Right, so you can find that directly if you don't want to use that notation. Right. Another way to look at this t-score, this would be the same thing as t sub 0.99, right? Because the area to the right of this would be 99%. So you could use t sub 0.99 notation as well, right? So t sub 0.99 would also be equal to that value. All right, so then part D, we want to find the critical t-value that corresponds to 90% confidence. Assume 20 degrees of freedom, right? So we're trying to find t, the critical value, t sub alpha divided by 2, where we have degree of freedom equal to 20. Right, so, if it helps you, please, draw a picture. Here would be 0, it'd be my t distribution. I'm going to have 2 marks over here. Where this is t alpha divided by 2, and this is negative t alpha divided by 2. And I want 90% confidence, so I'm going to have 90% area in between those two guys. So that leaves 5% here and 5% here, right? So in other words, t alpha divided by 2 is the same thing as t sub 0.05, right? Because this area to the right would be 5%. So this is equal to t sub 0.05. So I can find that using StatCrunch. Right, so my degrees of freedom was 20. I want the area to be 0.05 to the right. So we get 1.725, right, rounded to 3 decimal places. Okay. So then, now that we have like more familiar understanding of the t-distribution, let's look at computing a confidence interval, right? So when you're doing a confidence interval for mu, we're using the t-statistic. So you can see here in this statement that this is often referred to as the t-interval then, right, since we're using t. So we do have our standard 3 conditions that we've looked at, right? So we're assuming that our sample data is going to come from a simple random sample or randomized experiment. The second condition, right, is that the sample size is small relative to the population. So in other words, we want less than 5% of the population size in our sample size. And then we want the data to come from a population that's normally distributed, or the sample size needs to be large, right? And remember, large meaning that n is greater than or equal to 30. Right? So one of those two should be satisfied. So you can see there's the equation for the lower bound and the upper bound, and t alpha divided by 2 is my critical value with n minus 1 degrees of freedom, right? So you can see then this is the equation for the margin of error E, right? We're taking the critical value times the standard deviation of x bar, which is s divided by square root of n. Right? So now what we want to talk about is this normality condition. So you can see here, if you read in the text, Gosset is a mathematician that dealt a lot with this work. So it says when Gosset developed the t-distribution, he assumed the sample data came from a population that is normally distributed. But most distributions are not exactly normal, so we need to verify that the sample data appears normal enough before using the t-distribution to construct confidence intervals for the population mean. So we have 2 options to do this. The first option is the better option. So remember that if n is greater than or equal to 30, then we're good, right? We don't have to worry because my sample size is big enough to satisfy the law of large numbers and the central limit theorem, meaning that the distribution of x bar is going to look, normally distributed no matter what the population look like, right? But if we don't have, if we have a smaller data set, less than 30, the best option for us is to, check the normality condition using a normal probability plot and also a box plot to check for outliers, right? So what we're going to look for is we want the normality probability plot to conclude that it looks that the population was normally distributed, and then also we want to make sure that there's no outliers when we make the box plot, right? So we need both of those things to be satisfied. So if you don't want to do it that way, right, that's the preferred way. The option 2 is going to rely on what we call the robustness of construction confident intervals using student's t-distribution. So an inferential method is robust if it's accurate despite minor departures from its underlying assumptions, such as the assumption of normality in student's t-distribution. Right. So in other words, if a couple of our assumptions aren't met, is the method robust enough? Is it okay to still be somewhat accurate? Right. So if n is less than 15, or if 15 is less than or equal to n less than 30, we have some different options here, right? So we need to make sure that there's no skewness going on left to right if n is less than 15, and also we need to make sure that there's no outliers, right? So we're going to make a box plot to verify that. And then if n is in between 15 and 30, we just need to make sure there's no extreme skewness but no outliers, right? So there can be a little bit of skewness for 15 less than or equal to n less than 30, but we can't have a lot of skewness. Right. So then If n is greater than or equal to 30, we want to use students' t-distribution to construct confidence intervals, right? So we're good with that because of the central limit theorem and the law of large numbers. And then just to keep in mind, the reason why option 1 is better to use is it removes any subjectivity in determining whether a particular box plot is showing too much skewness or not, right? So option 1 is going to be a better fit for that. All right, so now what I would like to look at is example 2. So in both of these examples, there's 2 parts that we're going to look at. The sample size we know is n is less than 30. So we want to use the normal probability plot and also the box plot to determine if a t-interval can be destructed, right? So for these, I'm going to use option number 1, right? Because that's the better option to go, right? So remember, for option 1, we want to look at this normal probability plot. We want we want it to look like it's normally distributed, the population, and we want to look at the box plot and verify that there are no outliers, right? So for this first one, immediately, if you look at the box plot, there's one outlier here. So this is going to be a no. We shouldn't use a t-interval because there is an outlier, right? I'm going to know that right away. However, if you wanted to look at the critical value, right? So in other words, when you're evaluating the normal probability plot, remember that you're going to use table 6 in the appendix, and you're going to look up a critical value, right? So you're going to look up n equals 13 and find you get a critical value equal to 0.932, and this is less than r, which is 0.966, right? So since my correlation, my r value, is bigger than the critical value, then it looks like the population might be normally distributed, right? We could conclude that. But remember, there's the 2 conditions for this normality for the t distribution. So we didn't need to do that, but I was just doing that for practice, right? So you could immediately look at the box plot, see there's an outlier, and know that we can't use the t distribution, right? So like if I look at number 12, looking at the box plot, there's no outliers. From the box plot. And then if we look up n equals 9 in table 6, the critical value is equal to 0.912, and this is less than r, which is 0.997, right? So there's no outliers. The normal probability plot tells me that my distribution looks to be normally distributed. So the answer for this one would be yes, right? It meets both of those conditions, right, for option 1. Right, so you want to be comfortable verifying both of those. Right, so then example 3, it says a confidence interval has a lower bound of 18 and upper bound of 24. Determine the point estimate of the population proportion and margin of error from the confidence interval. Right, so we have a lower bound of 18, an upper bound of 24. I want to know what x bar equals and what e equals, right, the margin of error. So, if you think about it for a moment, right, you find the confidence interval by taking x bar plus or minus e, right? So you're adding, subtracting, you're going to get an equal distance on either side, right? Because if you have like a number line, here's x bar, here's going to be x bar plus e. Over here is going to be x bar minus e. So this distance is e units, and this distance is e units, right? So then what you end up getting is that x bar is going to be the midpoint, right? So remember how you find a midpoint, from algebra is you're going to average the 2 values, right? So we're going to take 18 plus 24 divided by 2. to find the midpoint, and this comes out to be 21, right? So x bar is going to be 21, right? Well, then there's a couple of ways you could find e then from here. You know, one way is that if you take x bar plus e minus x bar minus e, right, what this is going to give you is, well, and this is the, you know, upper bound minus the lower bound, right, if you don't see that, right? And then, so this would be equal to x bar plus e minus x bar plus e. So the x bar minus x bar cancel out, and then e plus e is 2e, right? So you end up getting 2e, right? So in other words, what this is showing you is that the upper minus the lower is equal to 2e. In other words, the width is equal to twice the error, right? So you could plug these values in and solve for e is one way to do this, right? So you could take 24 minus 16 equals 2e, and that would give you, 8 equals 2e. Wait, this should be not 16, this should be 18, sorry. So that would be 6. 6 equals 2e, and then if I divide both sides by 2, we get e equals 3. Right, so that's one way to do it. I mean, there's at least two other ways to do it. Another way is you could look at, you know, x bar plus e is going to equal your upper bound, right? And then you could plug in x bar, plug in the upper bound, and solve for e. That's the way I like to remember it. Or of course you could do x bar minus e equals the lower bound and solve that, right? So, you know, for example, we could have 21 plus e equals the upper bound of 24. So if I subtract 21 from both sides, you see that we get e equals 3 this way as well. Right. All right, so example 4, it says a simple random sample of size n is drawn from a population that is normally distributed. The sample mean x bar is found to be 50, and the sample standard deviation s is found to be 8, right? So x bar equals 50, s equals 8, and we know that the population is normally distributed. Right, so since the population is normally distributed, the n value doesn't matter here, right? We know it's normally distributed, but we do need to know the n value so that way we can calculate the degrees of freedom, right? So like looking at part A, we want to construct a 98% confidence interval for mu if the sample size n is 20, right? So I know that n equals 20. That means the degrees of freedom is going to be equal to n minus 1, which is 20 minus 1, which is 19. And so the t critical value that I'm going to need to find for a 98% confidence interval is going to be t sub 0.01, right? So that's equal to my t alpha divided by 2. Right, so remember, if I take 100% minus 98%, I'm getting that alpha value, right? So so that would be 2% left over, so 2% divided by 2% is 1%, right? So we get t sub 0.01. Right, so I need to calculate this value. So I'm going to use my t calculator in StatCrunch. So my degrees of freedom, we calculated to be 19. I want the area to the right, and I want that area to be 0.01. So my t critical value is 2.539. Right, if I round to 3 decimal spots. Right, so to construct my confidence interval, I'm going to take x bar plus or minus t alpha divided by 2 times s divided by square root of n. Right, so I should be able to plug these values in now. So x bar is 50. My t alpha divided by 2 was 2.539. And s is 8. And n is 20, so this would be square root of 20, divided by square root of 20. So if you plug this in your calculator, so I like to do 50 minus 2.539 times 8 divided by square root of 20, and then get that answer, and then do second entry, and then just change the minus to a plus, right? And then you can find the lower bound and the upper bound. Right. So let me get my graphing calculator to load really quick, and I will show you what I mean. I think I showed you this in the last video, so I'll remind you what I mean. Right, so got my graphing calculator here, so I just need to fill in some things. So I can plug in 50 minus 2.539 times 8 divided by square root of 20. Hit enter. And we get 45.48 roughly. And then I just like to hit second and then enter, second entry, and then just come up here and change this minus to a plus, right, to get the upper bound. And we can get both of those values. That's the easiest way to get those. Right, so the upper bound was 45.458, and the upper bound is 54.542. Right? So that's what we get doing that by hand. So now what I'd like to show you is how to find this using StatCrunch. Right, so using StatCrunch, you're going to go to Stat, and then T-Stats, and then one sample, and then we're going to go with Summary because we don't have the data. We have a summary. And then I just need to fill in these this information. The sample means 50. The standard deviation is 8. The sample size for part A is 20. We want to do a confidence interval, and we want a 98. So I need to change this to 0.98. And then hit compute. And then we get the upper and lower limits here. Right? So using StatCrunch, we get 45.457 and 54.43. 543. Right, so remember, you can also show confidence intervals with interval notation like this instead of writing lower bound and upper bound. Right, those were the two ways. Still applies here. Right. So then in part B, the only thing we're changing is the sample size, and we want to think about how does changing the sample size affect the margin of error E. Right. So n equals 15. So my degrees of freedom is going to be n minus 1, which is 15 minus 1, which is 14. I'm going to need to know that. So then my t critical value for 98% is still going to be 0.01, but you want to note that it's not going to be the same t-score as up here, right? Because my degrees of freedom is different. So that means my curve looks a little different. Right, so I'm just going to go back to my T calculator. So I need to change my degrees of freedom to 14 here. And I want this to be 0.01. And we get a critical value of 2.624, right? Right, so don't forget this is T alpha divided by 2, my critical T-score, right? So then to find the confidence interval, remember we're going to take x bar plus or minus T sub alpha divided by 2 times S divided by square root of n. So x bar is 50. My critical T-score was 2.624. And this would be times S, which is 8, divided by square root of n, which is 15. So if you using your calculator, you can calculate that lower bound and upper bound. So the lower bound is 44.580 if we round to 3 decimal spots. And the upper bound is 55.420, right? And if you want, validate this with StatCrunch as well, you can. Right, so we would open up the one sample T summary. Go to edit. I need to change a couple things so the mean's the same, standard deviation is the same. My sample size changed to be 15. Right, still 98% confidence interval. Hit compute, and you get those two scores there. The upper and lower limit. Right, so using StatCrunch, you should get 44.579, comma 55.421. Right, and again, you'll notice that these are a little different, and that's because of the rounding of T alpha divided by 2. Right, so using technology is more accurate. They're both correct. Right. So what we want to do is compare the intervals between these two guys and see what happened to E. Right, because remember, when you're finding the confidence interval, you're taking the point estimate plus or minus E. Right, so if you compare these, in part B, the confidence intervals are wider, right? A little bit wider. So that means that E increased, right? Because you're adding and subtracting a bigger number then, right, to make it wider. So decreasing N made E increase, right? And we know that because the confidence interval is wider. Right? So then in part C, we want to construct a 95% confidence interval for mu if the sample size n is 20. Right? So basically we're repeating part A, but we're just changing between 98 to 95% confidence interval. Right, so let me split up my page like I did in part B. So n is 20, which means my degrees of freedom is equal to n minus 1, which equals 20 minus 1, which is 19. Right? So my T alpha divided by 2 this time is going to be T sub 0.025. Right? And that's because I want a 95% confidence interval. So 100% minus 95% is 5%. Divide that by 2, we get 2.5%. Right? So that's my alpha divided by 2 is 0.025. Right? So we can find that using StatCrunch. I need to go to my T calculator. degree of freedom is 19. And I want the area to the right to be 0.025. And I get that t-score then, 2.093. Right, so then I need to take x bar plus or minus t alpha divided by 2 times s divided by square root of n. So we would have 50 plus or minus 2.093 times 8 divided by square root of n, which is 20. Right, so again, if you plug that in your calculator like I showed you, you can get the lower and upper bound fairly easy. So the lower bound is 46.256 and 53.744. And if you use StatCrunch, right, you'll get 46.256 and 53.744. So these came out to be exactly, if you round to 3 decimal spots, they worked out to be exact, right? So if I compare this interval to the one from part A, you'll notice that the interval is narrower in part C, right? It's tighter, right? So like the lower limit is 45 point something, and this is 46 point something in part C, right? So we got narrower. So decreasing the level of confidence made E decrease. Right? We can see that because the confidence interval is narrower. Right? So then in part D, it says, could we have computed the confidence intervals in part A through C if the population had not been normally distributed, right? So remember originally we were told that. So the answer would be no. The sample sizes are too small, right? In other words, we would have n less than 30 each time, right? So we don't have the data to see if options 1 and 2 then for normality would work or not, right? So therefore we couldn't do it. Right? So now we look at example 5. So example 5, we're told a simple random sample of size n is drawn. The sample mean x bar is found to be 18.4. And S, the sample standard deviation S is found to be 4.5. So in part A, we're asked to construct a 95% confidence interval for mu if the sample size n is 35, right? So n is 35. Degrees of freedom would be n minus 1, which is 35 minus 1, which is 34. So 95%, I'm looking for t sub 0.025. Right, so using StatCrunch, you can find this to be 2.032. And then so for the confidence interval, right, we're going to take x bar plus or minus t alpha divided by 2 times s divided by square root of n. So if we plug these values in now, we would have 18.4 plus or minus t.032 times 4.5 divided by square root of n, which is 35. Right, so plugging that in, we'll get the lower and upper bound. So the lower bound turns out to be 16.854, and the upper bound is 19.946. So in part B, it says if the sample size is n equals 15, what conditions must be satisfied to compute the confidence interval, right? So if n equals 15, the population must be normal. Right? Remember, that has to be the case if n is less than 30. Right? So now, example 6, it says the trade magazine QSR routinely checks the drive-through service times to fast food restaurants. A 90% confidence interval that results from examining 607 customers in Taco Bell's drive-through has a lower bound of 161.5 seconds and an upper bound of 164.7 seconds. Right? So in other words, n equals 607. I did a 90% confidence interval and got 161.5 comma 164.7. So what we're trying to find is what's the mean service from the 607 customers then, right? So in other words, what's the sample mean, x bar? Well, remember, that's going to be equal to the midpoint between the lower and upper bound, right? So we would just average. So we take 161.5 plus 164.7, so we're going to average the lower and upper bounds. And this comes out to be 163.1. So then part D says part B says what's the margin of error for the confidence interval, right? So remember, x bar plus e is going to equal the upper bound. So if we plug in what we know that x bar is 163.1 plus e, what we're trying to find, that's equal to the upper bound of 164.7. So then I can subtract 163.1 from both sides, and I find e to be equal to 1.6. Right, so then now we want to interpret this confidence interval that we were given. So we can say that we are 90% confident the mean drive-through service time at Taco Bell is between 161.5 seconds and 164.7 seconds. Right? So similar way to interpret it from last section, right? So again, this section is pretty similar to the previous section, just a little differently. Right? So now we'll look at example 7. So it says the following data represents the age in weeks at which babies first crawl based on a survey of 12 mothers conducted by Essential Baby. So that's a website, essentialbaby.com. So we have the data here. And in part A, we want to use either option 1 or option 2 to verify the requirements for constructing a confidence interval for the population mean are satisfied, right? So, one condition is we need the data to be collected randomly. So we're going to assume that this is true, right? Because it says there was a survey done, and we'll just assume that the people doing it did it correctly, right? Did like a random sample. The second thing is that we need the population size, or the sample size to be less than 5% of the population size, right? Well, n equals 12, so that's a really small number. So that's definitely going to be satisfied, right? The number of babies in America, if we want to stick just to the U.S., is definitely going to be large enough where that's not going to matter, right? So we don't have to worry about that so much. So that's why part A is really focusing in on option 1 or option 2, which remember that focuses in on the normality piece. Right, so I'm going to use option 1. Right, so in option 1, we're going to need to do a normal probability plot and get a correlation coefficient, right? And if you look in table 6, the critical value for n equals 12, that's equal to 0.928, right? So we're going to need that to be true. And then we also need to look at a box plot for outliers. Right, so let's use StatCrunch to do this. And so I went ahead and already typed in the data here to save time. So you can pause the video here and type this in if you'd like. So I typed crawl at the top for my variable name and typed in the 12 numbers. Right, so remember, to get a normal probability plot, you're going to go to graph and then QQ-plot. You have to click on the variable, and then remember you have to check these two boxes, right? And then hit compute, and we get this normal probability plot, and we get a correlation in R value of 0.982, right? So R equals 0.982. Right, so since this value is bigger than my critical value of 0.928, then we're good, right? We it looks, appears to be normal. Right, in other words, the population, right? The population. Or we could say that the sample looks to be drawn from a normal distribution, right? From a population that's normally distributed, right? So then the next thing that we need to check here for option 1 is we need to look at a box plot. So I need to go to graph, box plot. Oops, let me minimize this. There. And then hit crawl variable and hit compute. And what we're looking for in the box plot is, are there any outliers, right? Are there any dots? And there are not, right? So there's no outliers. So both of those things are met, right? So remember, we need the 3 conditions to be satisfied, but I talked through the other 2 conditions and why that makes sense, that those are going to be okay, right? So then the next thing that we need to do is construct and interpret a 95% confidence interval for the mean age at which a baby first crawls. So I've done it a lot by hand and by StatCrunch. So I think for part B here, well, I'll go ahead and show you both ways, right? So doing it by hand, x bar, is plus or minus t alpha divided by 2 times s divided by square root of n, right? So far what we know is that n equals 12, right? We don't know what x bar are, and we don't know what s is. So we need to calculate those. We can calculate those using StatCrunch. So if I go here, oops. Right, remember, I'll go to summary stats column, hit crawl. We need to know the mean and the standard deviation. Hit compute, and we get those 2 scores, right? So the mean is 38.25, and the standard deviation, I'm going to round to 3 decimal places, so it's 10.001. Right, so x bar was 38.25, and s is 10.001. Right, so since n equals 12, right, my degrees of freedom is going to be n minus 1, which is 12 minus 1, which is 11. So I need to find the t sub 0.025, since it's 95% confidence interval, with degrees of freedom equal to 11. Right, so I got to go back to my t calculator, degrees of freedom, change that to be 11. I want the area to the right to be 0.025, and we get 2.201, right, for rounded 3 decimal spots. Right, so then what I'm going to do is take 38.25 plus or minus 2.201 times s 10.001 divided by square root of n, which is 12. Right, I'm going to use that to get my lower and upper bound. Right, so then if you plug that in your calculator, you get 31.896 for the lower and 44.604 for the upper. Right. All right, so now let me show you how to get the confidence interval just using StatCrunch only, because it is a little different since we have the data instead of the summary of the data, right? So you're going to go to stat, tstat still, and you're going to go to one sample, and then you're going to go with data, right? So you're going to click on the variable and hit check mark this box, the confidence interval, and we want that to be 95%, right? That's right how it is. Hit compute, and then you get the lower and upper limit, right? So that matches with what we just got, right? Exactly if you round to 3 decimal spots. Right, so that's how you can find it using StatCrunch. So then one thing that we didn't do yet for this question was the interpretation. So let me write up the interpretation. So we could say that we are uh, 95% confident the mean age at which babies first crawl is between 31.9 weeks and 44.7 weeks. Right. Or I guess we would say 44.6. Right, not 7, because I was just rounding to 1 decimal spot. Right, all right, so ready for the last objective, and it's the last page of the notes. So we want to determine the sample size needed to estimate a population mean within a specific margin of error, right? So this is something similar that we did last time in the last section. So in order to determine the sample size, we're going to use this equation, right? And one thing you want to notice is we're actually using the z distribution instead of t. And that's because the t distribution depends on the degrees of freedom. In other words, depends on the sample size. And we don't have, we don't know n. That's why we're trying to calculate. So that's why we have to use the z distribution instead. Right, so you can see that, n equals, and we're going to round up, so we're taking the ceiling, right? So you're going to take the ceiling of z alpha divided by 2 times s divided by e quantity squared, take the ceiling of that, right? This is essentially what we're going to do. So in number 39, we're doing 2 parts. The first part is, so if you're reading through this, it says Dr. Paul, I'm not sure how to pronounce that, Ozweekmiski, maybe, wants to estimate the, we'll call him Dr. O, wants to estimate the mean serum HDL cholesterol of all 20 to 29-year-old females. How many subjects are needed to estimate the mean serum HDL cholesterol of all 20 to 29-year-old females within 2 points with 99% confidence, assuming that S equals 13.4 based on earlier studies, right? So, that's the first question, right? So let's focus, let's stay here, right, with this question. Then there's another part that I'll highlight in yellow here, right? There's two parts. Right, so reading the first part, we're told that we want to be within 2 points, so that would be the margin of error, right? We want the E to be 2. We want a 99% confidence interval. We're told that S equals 13.4. So my Z alpha divided by 2, my critical Z score, that's going to be Z of 0.005, right? Because you would take 100% minus 99%, which equals 1%. And then if you take 1% divided by 2, that's 0.5%, which is equal to 0.005. Right, so that's alpha divided by 2. Right, so in other words, that's alpha divided by 2. Right, so if you use, you'd have to use the normal calculator. Right, so you would go to stat calculators. We would want the normal calculator because we're using Z. So mean standard deviation, we're going to leave that as 0 and 1. We would want this to be greater than, and this area to be 0.005. Right, and we get that value, which is about 2.576. So then now we're ready to plug things in. We would have N equals the floor, or excuse me, the ceiling of 2.576 times 13.4 divided by 2, quantity squared. So if we simplify the inside part, that comes out to be 297.87998, right, and some more decimals. We don't really care about that, right, because we're taking the the ceiling of it, so that's just going to go up to be 298. Right, so using that equation by hand, we're getting an N value of 298. So, you can get an N value using StatCrunch as well. Remember, they're going to be a little different. But to do this, you're going to go to Stat, and then T-Stats, and then go to one sample, and then go to with sample size. So the confidence level, you're going to type in 0.99, right? So we're doing 99% confidence interval. The standard deviation is 13.4. And the width, remember, is 2 times E, right? So E was 2, so 2 times 2 is 4. So the width is 2 times E. Hit compute, and we get a sample size of 302, right? So it's a little off from what we calculated by hand of 298. But it's because of rounding error, right? Rounding this Z alpha divided by 2. Right, so using StatCrunch, we got 302. Right, so then now what we would like to do is the part in yellow. What if we want to do a 95% confidence interval, right? So in other words, we'd be finding Z sub 0.025, right? Because 100% minus 95% is 5%, and then 5% divided by 2 is 2.5%, which is 0.025 in decimal form. So that's the first thing we need to find. that z-score, critical z-score. So I need to be at my normal calculator. So I should already have one open here. Yep, here. So I want this area to be 0.025, and we get 1.96 roughly, right? Which, again, that one's pretty popular. You should begin to know that one by heart, right? So using the equation, we would have n equals the ceiling of 1.96 times 13.4 divided by 2, quantity squared. So if you simplify the inside, you'll get the ceiling of 172.449, which that, of course, would go up to be 173, right? Because with the ceiling, you always go up to the next integer, right? And then if you use StatCrunch, you'll get 175, right? So it comes out to be pretty similar, right? So the question says, how does the decrease in confidence affect the sample size required, right? So notice if we decrease the confidence level, the n value decreased, right? We went from 298 down to 173, right? So decreasing the confidence level decreases the sample size needed. All right, so that's all I have for this section. Thanks.